Um, so the first thing I was gonna do, if we had a little bit more time, was go over the unit circle.
I did that like a week ago.
Yeah, I was gonna say you've probably been doing it since you've been in the classroom this semester. So we don't need to necessarily go over that, but note for the praxis, having that down will make life a little bit easier on you. Not that the questions like will specifically ask, tell me sine of 30 degrees or tell me sine of 2 pi over 3 or whatever, but knowing that can make solving some of the problems a good bit easier.
Yeah.
So having that down will improve your life on the praxis anyway. And also just in general, because it's good to know the unit circle. Yeah. So I have a couple problems for us to look at. The first of which I think you're going to be able to answer with no trouble. So let's say we have a rectangle that we know is a rectangle.
Okay.
Actually, it's drawn this way on the test. I'll try to do it exactly the same. This is D, this is 40 degrees, and this is 60 meters. Okay. And it asks, in the rectangle above, what is the length of the diagonal D to the nearest tenth of a meter. Okay. Can you read what I'm writing on the board?
Yeah.
Okay. So you're asked to figure that out. So any ideas? I bet you can tell me how to do this.
The law of sines is what I'm going to use.
Okay. So tell me how you might use the law of sines.
Okay, so I did 60 over sine of 40 is equal to D over sine of 90.
All right.
We're going to
go on.
Yeah, and then we're going to multiply by the sine of 90 on both sides, and that'll give us D.
Good. So you get D equals 60 over sine 40 times sine of 90 degrees.
Yep.
Right?
Yep.
That will absolutely work. Can you tell me what sine of 90 degrees is?
I think it's 1, right?
Yeah. Yeah. So this is just the same as 60 over sine 40 degrees, which you'll notice point something out here. Like the other way you could think about this is notice that we have what type of triangle here?
Right triangle.
It's a right
triangle too.
What's that?
We could have just used SOHCAHTOA too.
Exactly. So the other option is to just notice, I know the opposite, I want the hypotenuse. So to say sine of 40 degrees is equal to 60 over D.
Yeah.
Solve that for D. So you're going to D sine 40 degrees equals 60. Solve for D and you get the same thing we already expressed, right?
Yep.
Okay. So law of sines absolutely works because it's a 90. It's because it's a right triangle. We don't necessarily need the law of sines. We can just use the right triangle ratios to solve it. And what is 60 divided by sine 40 degrees? You got to calculate, figure that out for me?
Oh, hold on, let me go get my calculator.
Oh, it's okay. We can do it together. Get my calculator out.
I got one of those like calculator emulators or whatever on my cell phone, and that's what I'm using for my video thing. Kind of got me off guard.
That's all right. So we'll just we can put it in here.
Okay.
and I get 93.3, which is the fourth option on here.
Okay.
The four choices were A, 71.5 meters, B, 78.3 meters, C, 80.5 meters, and D, 93.3 meters. Okay. So does that look okay to you? Awesome. One other thing that you could always remember, this one they were smart in the way they gave you the measurements, but in a right triangle, the longest side is always the hypotenuse. So if you happen to get one of these that was smaller than 60, you could just immediately mark it out and not have to worry about it, right?
Yeah.
So the larger sides opposite the larger angle in the triangle. So does this one seem good?
Yep.
All right, cool. Let's do another one then.
Are these problems from like previous practices?
These are from a practice test that's not published by ETS, but is a pretty they're fairly representational of what you might see on there.
I don't know. I've taken it twice and I ain't seen nothing this easy.
That one was easier than most. So the next one is a little bit. You tell me how it works. All right.
Yeah.
If it's better for what you're talking in your experience. So which of the following is an identity for trigonometric expression? Tan sine of 4 theta cosine of negative 4 theta. Does that look all right?
Yep.
Does that look more like the speed of what you've seen so far?
Oh, yeah.
So, any ideas about what you might want to do first?
No clue. I haven't messed with identities since 10th grade.
Okay. So so there's a few things that we can go off of. So trying to think the best way to start. First of all, let me show you this. You already know that you get a formula sheet. That's what I'm trying to say.
Oh, yeah, yeah. Definitely do get one of those back.
Yes, it's very helpful to have. And here's an example of what you might see. Hold on, I'm making sure that I have it up here ready to go.
I think it's on like Google Pages or something.
Yeah, it is here. I mean, you can see it. So,
yeah.
So it should look like this, right? And you get this whole set of formulas here for notations, and then definitions, and then you get these formulas right here. The ones that are particularly interesting for our purposes are the ones related to trig right here.
Yeah.
Okay. So you get these half angle formulas, you get these sum angle formulas. It gives you the range of inverse trig functions, gives you the law of sines and law of cosines. And that's pretty much it, right?
Mm-hmm.
Luckily, that's a lot. That gives you a good bit of information to go off of. because the sum angle formulas, once you have these right here, you can really figure out a lot of other trig identities from those. Okay.
Mm-hmm.
So for instance, we know that sine of x plus y is equal to sine x cosine y, right? Plus cosine x sine y. With me there?
Yep.
Now you might notice that both of these are in the same spot, right? They have this. Yeah. They're almost the same number. Oh wait, I'm pointing at the board and you can't actually see what I'm doing. So let me stop screen sharing. We have x and y. Here we have 4 theta and negative 4 theta, so they're almost the same thing. So we might think of something like the double angle formula. If we want to know the double angle formula, all we have to realize is that sine of 2x is just sine of x plus x, right?
Yeah.
And so you can just say sine x cosine x plus cosine x sine x, which is just sine, it's just 2 sine x cosine x, right? You with me there?
Yeah.
And you can do the same thing with the cosine formulas. You have to remember with cosine that it's plus minus on one and minus plus on the other side. Let me show you what I mean. Again. So if you look at the cosine formula, where you have cosine x plus minus y, cosine x cosine y minus plus, so you have to kind of keep the minus and pluses straight. But you can do the same thing with the cosine formulas there. If you want a double angle formula, just do x plus x.
Oh, okay.
Does that look all right?
Yeah.
Now, if you look at this, the one thing you can do, if you're just completely stuck, you can look at these formulas here and say, what has anything that looks close to what I'm talking about? And so one thing I notice is that the expression I'm given has a sine and a cosine in it. Right?
Yep.
So if it has a sine and a cosine, that might lead me to look at the sum angle identity for sine, because it has sine times cosine in it. You follow me on that?
Yeah.
Okay. So if I'm thinking about this sine identity, then I notice that I have a sine and a cosine here. It would be really nice if I had just a sine, if I had a sine 4 theta, cosine 4 theta, instead of cosine of negative 4 theta. You with me there?
Yeah.
Okay. So, how might I find my way around that? Well, what do you know about cosine of a negative number? Do you know anything about that? So cosine and sine, as far as even and odd go, do you know what I mean when I say an even and odd function?
Yeah, sine's the odd function, and then cosine's the even function.
That's right. So just as a recollection, even function is where we have. Wait, I'm trying to remember if you said this right or not. But f of the opposite of x is the same as f of x, right?
Yeah.
And an odd function, we have f of the opposite of x equals the opposite of f of x. So an even function, if we look on either side, if we go x and the opposite of x, we get the same output values. X and the opposite of x get the same output values. So this thing's going to be symmetric over the origin. I'm sorry, over the y-axis is what I meant to say. Okay? Symmetric over y-axis. An odd function, on the other hand, if you go out x and the opposite of x, you're going to get opposites for the outputs. You go x and the opposite, you're going to get opposites for the output. So this thing's going to be symmetric over the origin, or about the origin, what I should say. Does that make sense?
Yeah.
Okay. So if we just think about what sine and cosine look like, sine looks like this.
Mm-hmm.
Its symmetry is about the origin. So sine is an odd function. Cosine, on the other hand, looks like this. So it's symmetric about the y-axis.
Mm-hmm.
Is that all right?
Yep.
Okay. So that tells me this guy up here I can rewrite as 10 sine of 4 theta cosine of 4 theta.
Yeah.
Because they're just going to be the same. Well, cosine's an even function.
Yeah. It's going to turn positive.
Exactly.
Yeah.
So this looks an awful lot like that thing right there.
Yeah.
Where we have sine x, cosine x. What's the x in this case?
4 theta.
That's right. So, in other words, so if I want it to look exactly like that, I need that 2 here. So I might notice the 10 is 5 times, and then I have sine 4 theta, cosine 4 theta. Right? You with me there?
Yeah.
And so how can I rewrite this 2 sine theta, cosine 4 theta, 2 sine 4 theta, cosine 4 theta? It's going to be the same thing as sine of 2x.
So it'd be 5 times sine of 8 theta.
Exactly. Okay. And it turns out your choices on this one are 5 sine of 4 theta, 5 sine of 8 theta, ding, ding, ding.
Yeah.
10 sine of 8 theta, and negative 5 sine of 4 theta. Okay. So even the choices might give you a hint. Maybe I should look at the double angle formula.
Yeah.
Okay. Now, there is another possibility here. If you're not sure about the, you can always try angles and see which ones match up.
Yeah.
Since you have a multiple choice. This is the workaround for a multiple choice test.
Yeah.
I would,
plug in the
what's that?
Could you not just plug in 10 sine of 4 theta cosine 4 or negative 4 theta, and then just plug in the answers if you get like the same thing, like if you just made up a value for theta?
Yes, that's what I'm saying. Is you could you would want to choose it carefully. Like you don't want, for example, you would want to do pi over 2.
Yeah.
Because 4 times pi over 2 gives you 2 pi. And 8 times pi over 2 gives you 4 pi. And 2 pi and 8 pi, you understand what I'm saying there? You might not want to do something that where sine's going to give you 0. So they're going to match up in that case because you're going to get 0 for both of them.
Yeah.
You understand what I'm saying?
Yeah.
So choose something. You want to choose smart. That's what I'm saying.
Yeah.
But
so
yeah, that's the test taking strategy way to do it.
Yeah, just put it in and then match up the choice.
Yeah. But, you know, knowing to look at sine and cosine makes me think of this guy right here. That's the understanding trigonometry way to do it.
Yeah. Yeah.
So, does that sound good?
Yeah.
All right. Questions on that one?
I haven't seen that in so long.
Okay.
Although I've seen the odd and even part, but I didn't know what that did.
Okay.
Like I didn't know what that did for me.
Yeah. So that's what it. This right here is what it does for you. If you the even and odd idea is really has to do with symmetries, and if you take in opposite inputs, what's the impact? Okay.
Yeah.
So it's nice here because you can say cosine of the opposite of 4 theta is just going to the same as cosine of 4 theta because cosine is an even function. We know that it's symmetric over the y-axis like that. Go the same distance in either direction, you get the same outputs. Okay. Yeah, there's a lot there with that problem, which is nice.
Heck yeah.
Okay, so let's do another one. All right, so here I'm going to read this one to you, and then I'm going to share a screen so you can see a graph that is provided with this. Okay.
Yeah.
It says the graph above shows a representation of a sound wave on an oscilloscope. Describe the function that best models the curve. Okay. So we're basically saying, here's a sound wave on an oscilloscope. What function models the curve? And our choices are a sine function with amplitude 2.
Ooh, that's what I'm doing this week.
Good. Period 2 pi. And phase shift of pi over 3 to the right of the origin. B is cosine function. And I'm going to start abbreviating here with amplitude 2, period 2 pi, and phase shift pi over 3 to the right of the origin. C, sine function with amplitude 2, period 2 pi over 3, and phase shift 5 or 6 to the right, and D, cosine with amplitude 2, period 2 pi over 3, and phase shift pi over 6 to right. Okay.
Okay. So we're really looking at the period and the phase shift.
Yeah, we have amplitude, period, and phase shift. So here's what the graph looks like. Let me share my screen. So here you go. So this is the graph that you see on the sheet. Okay. So even without knowing any of this stuff right here, can you pick off some characteristics of that function? What can you tell me?
It definitely has an amplitude 2, and then we got
definitely has an amplitude of 2. So just for the viewing audience, Tell me how you know that it has an amplitude of 2.
Well, it goes from 2 to -2.
Uh-huh.
And so the absolute value of that of 2 is 2.
Yeah, so
Like
we have our amplitude goes from the midline to the
to the
max,
top.
and the midline to the bottom. So right, so
Yeah.
that's kind of our wave height in some sense.
Yeah.
So the amplitude is definitely 2. That's not going to help us a lot here because the amplitude for all of these is 2, right?
Yeah.
Okay, so what else can you tell me?
It's definitely shifted over to the right. Pi/6.
So why is it shifted over to the right pi/6?
Well, because the sine wave starts. Oh, it could be a cosine wave. I was thinking of sine. So a sine wave starts at 0, and this
Right.
one starts. Yeah. So it's at 0 at pi/6,
Uh-huh.
right? So
So a
could
sine
be.
definitely starts at its midline. So we would think about a sine curve starting here,
Yeah.
and then moving over. But it could be a cosine curve shifted over as well, right?
Yeah, it could be shifted over. What is that? Pi/3.
Right. It could shift over because the cosine starts at its maximum. It could shift over pi/3 this
Yeah.
direction. What about the period? What's the period?
So if we're talking about a sine, I guess it's okay, it goes from ooh, uh, okay. So I guess the period would be it was a sine curve. Uh, would it be just pi?
Well, let's think about it. It turns out it does not matter whether it's sine or cosine. The
Oh, okay.
period is the same regardless. So the period is basically how long it takes to repeat, right? If you
Yeah.
shift it over by that amount, it should look the same. You with me
Yeah.
on that? So, for
Yeah.
example, we might go from -pi/3 to +pi/3. That's one period because that is one full, uh,
Point.
that repeats over and over and over again. You with me there?
Yeah.
So from -pi/3 to +pi/3 is going to be 2pi/3. Notice if we go from 0 to 2pi/3, that would also represent one. If we took that block, it's a repeating block. If you did -pi/6 to +pi/2, that's also a distance of 2pi/3, and that's a repeating block. You with me on that?
Yeah.
So it doesn't matter how, like, even where you start. I could start like down here and pick up again right here. If I go over 2pi/3, I get the same output regardless of where I start. If I go over 2pi/3, I still get the same output.
Okay.
You with me on that?
Oh yeah.
So the period is gonna, that's not the way I want to do that. Let's say the period is gonna be 2pi/3. Okay. So that when we look at our possibilities here, it eliminates A and B, because they say the period is 2pi. The period of sine and cosine is 2pi, but this particular function has a period of 2pi/3, so it either has to be C or D. You with me there?
Mm-hmm.
Okay. And as you note, it could be. So let me do a little bit of review here. we know the amplitude changes if we start with, say, a cosine function. Okay. I need to do a vertical stretch on this in order to get the amplitude to match. Same thing if I start with a sine function, I need to do a vertical stretch to make the amplitude match. Okay. In order to change the period, I have to do a horizontal stretch or compression.
Yeah.
Now remember, I have to undo the operations on the input. Okay.
Yeah.
Something we talked about the last time I did one of these.
Yeah.
So if I multiply by 3, for instance, that's actually going to shrink it by a factor of 1/3, which is actually what I want to do, which was incidental. But you follow me there? Like I want to shrink it by a factor of 1/3 because I want to go from 2 pi to 2 pi over 3.
Now we need to shift it.
And so here's the sign. So both of these, so I could either shift the sine curve by a the sine curve pi over 6, or shift the cosine pi over 3.
You
with me on there?
Yep.
So the cosine I could shift pi over 3. Though I need to make sure I do that in parentheses to make sure I take care of the period before I do that. Or I could shift the sine curve. I wanted to go right, but it's going to have the same net effect. Pi over 3. Pi over 6. Pi over 6. Thank you. Yeah. So notice those all gave me the same thing, right? So I could either do a sine function with amplitude 2, period 2 pi over 3, and shifting right pi over 6, or a cosine function with an amplitude of 2, period of 2 pi over 3, shifting right pi over 3. So, given my options, obviously these two are out because they have the wrong period. This one has the wrong phase shift, so that's the one that's going to work.
Yeah.
It's not the only one that works, but it's the one of the options given.
Yeah, that's the one. Yeah.
Okay. Does that sound okay?
Yep.
Okay. Good. Any questions on that?
Nope.
Okay. You want to do one more before you have to go?
Yeah.
Okay. Let me see here. Let's find a good one to give you. So maybe we'll just do this one. So so the diagram that goes with this one has a clock with its center at the origin. It's going to be a bad drawing, but you'll have to just bear with me. Okay. So centers at the origin. It's numbered as a clock is traditionally numbered. Okay. And we have this hand pointing at 10. And we're told the hour hand has a length of 5 centimeters. Okay. And this angle is labeled as theta. Okay. It asks, what are the coordinates of the tip of the hour hand at 10 o'clock? Okay. And the possible solutions here are all given in terms of sine and cosine. So let me just go ahead and write them down here. the options given are 5 cosine of pi over 6, 5 sine of pi over 6, 5 cosine of 5 pi over 6, 5 sine of 5 pi over 6, 5 sine pi over 6, 5 cosine of pi over 6, and 5 sine of 5 pi over 6, 5 cosine of 5 pi over 6. Okay. Now, basically, there's a lot of information given here to kind of distract you from the question of you have a circle centered at the origin that has a radius of 5, right?
Mm-hmm.
You want to know the coordinates of this point right here. If it's at 10 o'clock, so I really should draw this kind of more over here. You with me?
Wait, the tip is on the circle?
Well, it's not at the tip of the clock, but it actually the coordinates of the tip of the hour hand. So what we're really concerned about is like the circle traced by the tip of the hour hand. I don't really care so much about the edge of the clock. You with me there?
Okay.
I really only care about that circle made by the hour hand right there.
Yeah. And then you can find that angle, the one closest to the origin.
That's right. So what would this angle be if that's at 10 o'clock?
So it'd be 180 minus whatever theta is.
Right. True.
Yeah.
So can you figure out what it would have to be?
I'm going to make an assumption of like maybe 30, 35-ish.
Okay. Well, let's think about it. What do you know this angle is right here?
Oh, that's definitely 90.
Or in radians?
Pi. Wait, pi over 2.
There it is.
Yeah.
So that's pi over 2. Now, we know that this is 12 and this is 9, right? So divide that into what size pieces?
Yeah, so I guess it is pi over whatever, 30 degrees. So
it's going to be 30 degrees, which is a third of 90, or it's 1/3 of pi over 2, which is pi over 6. Right?
Yeah.
Okay. Now, that means that theta is what?
5 pi over 6.
5 pi over 6, right? So theta is an angle in standard position. And, I mean, we know that this point right here, that if we have a radius r in a circle centered at the origin, we can always define sine of theta. So, and we also have to assume theta in standard position. Sorry, my board work is leaving a little bit to be desired right here. Sine of theta is just going to be the y value of the point divided by the radius. Cosine is going to be the x value of the point divided by the radius. Right? And this comes from just the, well, it comes from the way we can define these functions, but it's really related to what we did with right triangles. And it works. This is why the x and the y values are just cosine and sine of the unit circle, because there the radius is just equal to 1, right? Yeah. If you define them in the unit circle, you just have to use similarity to get these ideas right here. But we get to the point then is xy, which is r cosine theta, r sine theta. All right?
Yep.
So the angle that's in standard position is 5 pi over 6. So we're going to do r cosine of 5 pi over 6, r sine of 5 pi over 6.
Mm-hmm.
which is going to be option B over there.
No.
Okay. So, does that look all right?
Yep. Gosh, dog. Yeah, I just used all of these like here recently, so it's still fresh on my brain.
Good. That's awesome. That's fresh on your brain is helpful. So some other things real quick before we go that you might want to think about with EPS's review study guide. They give some overview of stuff that you need to know. And it says, so it talks about trig in general triangles, apply the law of sine and cosine. So when you mention the law of sine and cosine, that's actually something that's important to do. So working some problems with that.
Heavily hit that.
Yeah.
Right
things like arc length and with angles like we talked about with this last one, to be able to construct a tangent line,
Okay.
all that sort of stuff. Arc length and area measurements for trig is going to be very helpful to you. They give a whole list of trig. Well, within the functions section, they have understand how to construct the unit circle and how to use it to find values of trigonometric functions for all angle measures in their domains. So that we talked about is going to be useful to you at the very beginning, knowing the unit circle, understanding radian measure, domain, range, amplitude for sine, cosine, all that sort of stuff. Periodic phenomenon like we talked about, and then using identities as discussed. So anyway, those are things you might want to be thinking about reviewing as we go as you prepare for the test.
Yeah.
So hopefully that was helpful.
Dude, that was awesome.
All right.
Actually applying like the stuff that I'm getting like to a higher level than just the ground.
And it's reassuring.